Picture this scene from July 1st, 2025. Deep in the Chilean desert, the ATLAS survey telescope captures a faint point of light moving against the stellar background. Within days, astronomers realize they're looking at something that shouldn't exist according to conventional wisdom. The object, designated 3I Atlas, isn't just another asteroid or comet. It's a refugee from another star system, carrying with it the frozen memories of stellar neighborhoods we can barely imagine. The ATLAS system itself represents a remarkable achievement in automated sky surveying. Consisting of 4 telescopes spread across Hawaii and Chile, this network scans the entire visible sky every 24 hours, searching for anything that moves, changes brightness, or appears where nothing existed before. The system was originally designed to detect potentially hazardous asteroids that might threaten Earth, but it has become humanity's early warning system for all kinds of transient astronomical phenomena, from supernovae in distant galaxies to, as we now know, visitors from other star systems. Get ready. The journey begins now. The numbers alone should make your mind reel. This interstellar wanderer is following an unbound hyperbolic trajectory with an eccentricity of 6.141, making its path appear almost perfectly straight rather than curved. To put that in perspective, any object with an eccentricity above 1 is on a path that will never return to our Sun. Earth's nearly circular orbit has an eccentricity of just 0.017. Even Halley's Comet, with its highly elliptical 76-year orbit, only reaches an eccentricity of 0.967. 3I Atlas has the highest eccentricity of any interstellar visitor we've ever encountered, exceeding even the famous Oumuamua's modest 1.2 and 2I, Borisov's impressive 3.4. But here's where things get beautifully strange. Despite coming from the darkness between stars, 3I Atlas's trajectory is aligned with our solar system's ecliptic plane to within just 5 degrees. The ecliptic plane is the flat disk defined by Earth's orbit around the Sun, and most planets orbit within a few degrees of this plane. For a random interstellar object, the probability of arriving with such precise alignment is vanishingly small, a mere 0.2%. It's as if this ancient traveller somehow knew exactly how to thread the needle of our planetary system with surgical precision. This alignment raises intriguing questions about the object's origin and journey. Did it happen to be ejected from its parent star system in a direction that coincidentally matched our solar system's orientation? Or could there be underlying galactic dynamics we don't yet understand that preferentially channel interstellar objects along certain trajectories? Some researchers have even speculated whether the alignment could indicate intentional navigation, though such suggestions remain highly controversial within the astronomical community. What makes this discovery even more remarkable is the speed at which 3I Atlas is moving. When astronomers first calculated its velocity, they had to double-check their numbers. This object is racing through our solar system at roughly 60 kilometers per second relative to the Sun, making it the fastest interstellar visitor ever recorded. For comparison, Oumuamua moved at a relatively sedate 26 kilometers per second, while 2I Borisov cruised along at 32 kilometers per second. To put this velocity in more familiar terms, 3I Atlas is traveling at over 216,000 kilometers per hour, fast enough to cross the entire width of Earth's orbit in less than 40 days. At this speed, the object could travel from Earth to the Moon in less than 2 hours. The Voyager probes, humanity's fastest spacecraft, took decades to reach the outer solar system. 3I Atlas will pass through in months. This breathtaking velocity tells a story written in the language of celestial mechanics. 3I Atlas has been drifting through interstellar space for potentially billions of years, its speed gradually increasing through gravitational encounters with countless stars, stellar remnants, and the invisible architecture of dark matter that shapes galactic structure. Every close pass by a massive object added momentum to its cosmic journey, ratcheting up its velocity like a pinball bouncing between stellar bumpers across galactic distances. The gravitational slingshot effect, first deliberately used by human spacecraft designers in the 1970s, occurs naturally throughout the galaxy. When a small object passes near a massive one, it can gain or lose kinetic energy depending on the geometry of the encounter. Over millions of years and countless stellar encounters, objects like 3I Atlas can accumulate enormous velocities through this process, eventually becoming some of the fastest moving matter in the galaxy. The implications of this extreme speed extend far beyond mere curiosity. Velocity is the signature of origin, the cosmic fingerprint that reveals where an object has been and what forces shaped its journey. 3I Atlas's record-breaking pace suggests it was ejected from its parent stellar system with substantial kinetic energy, possibly due to gravitational interactions with massive planetary bodies or close encounters between binary stars. The violence required to accelerate matter to such speeds hints at cosmic catastrophes we can barely comprehend. Astronomers can use the object's current velocity and trajectory to trace its path backward through the galaxy, attempting to identify its stellar system of origin. However, the uncertainties multiply rapidly as you go back in time. Gravitational perturbations from stars the object passed, the influence of the galaxy's spiral arms, and the poorly understood distribution of dark matter all affect the calculations. Current estimates suggest 3I Atlas may have originated from a star system anywhere from 50 to several hundred light-years away, narrowing down its birthplace to just a few million candidate stars. Consider the atoms that make up 3I Atlas. The hydrogen was formed in the Big Bang roughly 13.8 billion years ago, when the universe was just minutes old. The heavier elements, carbon, oxygen, nitrogen, and others, were forged in the nuclear furnaces of stars that lived and died before our sun was born. These stars, their names unknown and unknowable, enriched the interstellar medium with the raw materials for new stellar generations. Some of the atoms in 3I Atlas might have cycled through multiple generations of stars before finally condensing into solid form in the protoplanetary disk of its parent system. Each atomic nucleus carries a record of this journey in its isotopic composition, a fingerprint that reveals which types of stellar nucleosynthesis produced it. By studying these isotopes, we read a history written in the language of nuclear physics, spanning billions of years and light-years of space. The molecules being released from 3I Atlas's nucleus during its solar encounter carry within them the chemical fingerprints of stellar nucleosynthesis that occurred when the universe was younger, when different stars dominated the galactic neighborhood, and when the chemical composition of interstellar space differed significantly from current conditions. Every atom of carbon, oxygen, and nitrogen liberated from its icy matrix tells a story that began in the nuclear furnace of an alien sun and ends with us, curious observers on a small planet, trying to decode messages written in starlight and sublimating ice. The timing of our species' technological development seems almost perfectly synchronized with the arrival of these interstellar messengers. We've reached the threshold of capability necessary to detect, track, and study visitors from other star systems just as they begin appearing in our observational surveys with increasing frequency. This cosmic coincidence might reflect selection effects. We only notice interstellar objects now because we've developed the technology to detect them, but it also suggests we're entering a new era of astronomy. Within our lifetimes, the study of interstellar objects will likely transition from extraordinary events generating worldwide attention to routine observational programs. Next-generation survey telescopes like the Vera-C Rubin Observatory, scheduled to begin operations soon, will scan the sky with unprecedented depth and cadence, detecting interstellar visitors while they're still in the outer solar system. This early detection will enable detailed observation campaigns tracking objects throughout their solar passage, eliminating the observational gaps and uncertainties that plague current studies. Future space missions might even attempt rendezvous with interstellar visitors. A spacecraft positioned in the outer solar system could potentially intercept an incoming object, matching velocity and traveling alongside it as it approaches the Sun. Such a mission would provide unprecedented close-up observations, potentially including surface sampling or even landing attempts. The technological challenges are enormous. Matching the high velocities of interstellar objects requires enormous fuel expenditure, but the scientific rewards would be extraordinary. The study of interstellar visitors represents one of the newest fields in astronomy, barely a decade old, yet already transforming our understanding of planetary systems and galactic ecology. Before Oumuamua's discovery in 2017, interstellar objects were purely theoretical. Astronomers predicted they should exist based on models of planetary system formation, but none had been detected, despite decades of sky surveys. The discovery of 3 confirmed interstellar visitors in just 8 years suggests these objects are far more common than initially expected. Early estimates suggested we might detect 1 interstellar object per decade with existing survey capabilities. The actual detection rate has been roughly 3 to 4 times higher, implying either that interstellar objects are more numerous than predicted, or that they're larger and brighter than theoretical models suggested. Extrapolating from detection rates, astronomers estimate that at any given time, there might be several interstellar objects within Jupiter's orbit. We simply haven't detected most of them yet because they're small, dark, or not actively outgassing. The total population of interstellar objects in the galaxy likely numbers in the trillions, creating a vast reservoir of material connecting stellar systems across the Milky Way. This reservoir has profound implications for planetary science. Material ejected from one stellar system can potentially be captured by another, creating a slow but steady exchange of matter between systems. Over billions of years, this exchange could transport significant quantities of material across galactic distances. Some researchers have speculated that Earth itself might contain atoms that originated in other stellar systems, delivered by ancient interstellar visitors that impacted our planet billions of years ago. The composition of interstellar objects provides crucial tests of planetary formation theories. Do all stellar systems produce similar types of comets and asteroids, or does composition vary systematically with stellar properties? Are carbon-rich objects common, or is 3I Atlas an outlier? How does the ratio of icy comets to rocky asteroids in the interstellar population compare to our solar system's demographics? Each new interstellar visitor helps answer these questions, gradually building a statistical understanding of planetary formation throughout the galaxy. The detection and characterization of 3I Atlas showcase the remarkable technological advances that have revolutionized astronomy in recent decades. The Atlas survey system that discovered the object represents just one component of a global network of sky surveys that collectively monitor the entire visible sky every few nights, searching for anything that changes or moves. These automated survey systems generate enormous quantities of data, terabytes of images every night, that must be processed rapidly to identify transient events before they fade or move away. Modern machine learning algorithms sift through millions of detections, filtering out cosmic rays, satellite trails, asteroids, variable stars, and other mundane events to identify the rare objects of genuine scientific interest. The software that flagged 3I Atlas as unusual was trained on millions of previous detections, learning to recognize the patterns that distinguish interstellar visitors from solar system residents. Once identified, follow-up observations employ the world's largest telescopes and most sophisticated instruments. The James Webb Space Telescope, humanity's premier space observatory, has provided unprecedented infrared spectroscopy, revealing 3I Atlas's unusual chemical composition. The Hubble Space Telescope has captured high-resolution images despite the challenging observational geometry. Ground-based telescopes from Chile to Hawaii have tracked the object's motion with precision sufficient to refine its trajectory to within kilometers. Spectroscopy, the analysis of light split into its component wavelengths, provides the most detailed information about cometary composition. Different molecules absorb and emit light at specific wavelengths, creating spectral signatures as distinctive as fingerprints. By analyzing these signatures, astronomers can identify which molecules are present in the coma, measure their relative abundances, and even determine isotope ratios that reveal the object's formation conditions. The near-infrared wavelength range, where JWST excels, is particularly valuable for studying comets because many important molecules have strong absorption features in this range. Water, carbon dioxide, carbon monoxide, methane, and various organic compounds all produce distinctive near-infrared spectra. Space-based infrared observatories planned for the coming decades will complement JWST with different capabilities. Some will specialize in high-resolution imaging, potentially resolving surface features on interstellar object nuclei. Others will focus on time-domain observations, monitoring how brightness and composition change as objects approach and recede from the Sun. Together, these facilities will transform our ability to study interstellar visitors from distant, poorly understood curiosities to well-characterized samples of extrasolar matter. As October 29th approaches and 3I Atlas disappears behind the Sun's brilliant glare, we're reminded that the universe still holds secrets beyond our current ability to observe or understand. The perihelion mystery represents both the limits of our current knowledge and the boundless potential for discovery that awaits future generations of cosmic explorers. The final week before perihelion represents a critical observational period. Astronomers worldwide are collecting as much data as possible before solar conjunction makes observation impossible. Every spectrum, every image, every photometric measurement adds to the dataset that will be used to reconstruct what happened during perihelion. These pre-perihelion observations establish baselines against which post-perihelion observations will be compared, allowing researchers to identify any changes in composition, structure, or behavior. The comet's brightness has been increasing steadily as it approaches the Sun, following a power law relationship typical of comets. However, comets sometimes exhibit sudden brightness outbursts, brief periods of dramatically increased activity that can make them hundreds or thousands of times brighter than expected. These outbursts typically result from exposure of fresh, volatile-rich material or structural changes that suddenly increase the active surface area. If 3I Atlas experiences such an outburst during its final approach, it could become visible to the naked eye despite solar conjunction complications. Ground-based observers with access to large telescopes are attempting to characterize the comet's rotation state, surface properties, and activity patterns in as much detail as possible. Continuous monitoring over multiple rotation periods reveals how activity changes as different surface regions rotate into and out of sunlight. Some areas might be more active than others due to compositional differences or varying amounts of dust cover. Understanding these patterns helps predict how the nucleus will respond to increased solar heating at perihelion. Amateur astronomers are also contributing valuable observations. While their telescopes typically lack the light-gathering power and spectroscopic capabilities of professional instruments, they provide geographic diversity and time coverage that professional facilities can't match. A global network of amateur observers can monitor the comet continuously through Earth's rotation, detecting short-lived events that might be missed by professional telescopes scheduled in discrete observing blocks. The European Space Agency has announced that both Mars Express and ExoMars Trace Gas Orbiter will attempt additional observations as the comet recedes from Mars, providing a final Martian perspective before the observational blackout begins. These observations will help constrain the comet's dust production rate and search for any changes in activity since the October 3rd close approach. Whether 3I Atlas emerges from its solar encounter as a transformed comet, a fragmented debris field, or something entirely unexpected, it will have taught us something profound about the nature of matter, energy, and structure in the cosmic arena. The ancient ice and rock that began this journey in another star system will have completed a transformation that connects the physics of stellar neighborhoods, separated by dozens of light years and billions of years of cosmic evolution. The story of 3I Atlas is ultimately our story too, a reminder that everything we are and everything we see around us originated in the nuclear furnaces of stars, travelled through the cold depths of space, and eventually assembled into the complex structures that make life and consciousness possible. When we observe this ancient wanderer approaching the sun, we're not just watching an astronomical event, we're witnessing our own cosmic ancestry, written in ice and rock across the vast distances between the stars. We are made of star stuff, as Carl Sagan famously observed. Every atom in our bodies except hydrogen was forged in stellar nuclear furnaces or supernova explosions. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were created by stars and distributed through space when those stars died. In a very real sense, we are the universe becoming aware of itself. Matter organized in such a way that it can contemplate its own origins and evolution. 3I Atlas carries within its icy nucleus atoms processed by different stars, following different evolutionary paths under different cosmic circumstances. By studying this visitor, we expand our understanding of the diversity of stellar nucleosynthesis and planetary formation throughout the galaxy. We learn that while the basic physical laws operate the same everywhere, the specific conditions, stellar mass, metallicity, planetary system architecture, create enormous variety in the outcomes. The mystery of what will happen when 3I Atlas reaches the sun embodies everything that makes us human. Our insatiable curiosity about the universe around us, our determination to understand phenomena that operate on scales far beyond our direct experience, and our recognition that we are part of something infinitely larger and more complex than ourselves. In studying this ancient traveller, we study our own origins and our place in the cosmic order that has been evolving for billions of years before we existed, and will continue long after we're gone. This sense of cosmic context, understanding that we exist as part of a vast evolving universe full of wonders beyond imagining, enriches human existence in profound ways. It provides perspective on our daily concerns, reminding us that we participate in something grander than individual lives or even civilizations. It inspires humility before the magnificence of nature, while simultaneously celebrating the human capacity to understand and appreciate that magnificence. Tonight, as you step outside and look up at the stars, remember that among those distant points of light, other worlds orbit other suns, and occasionally, matter from those alien realms makes the incredible journey across the void to visit our solar system. In studying 3I Atlas, we're not just observing an astronomical event, we're participating in a cosmic conversation that spans the galaxy, connecting us to processes and possibilities that stretch our understanding of what it means to exist in this vast, mysterious, and potentially populated universe that we call home. The countdown continues. Somewhere in the darkness between Earth and Sun, 3I Atlas races toward its moment of truth, carrying with it questions that may reshape our understanding of visitors from the stars and our place in the vast cosmic community that surrounds us. The discovery of 3I Atlas and its predecessors has opened an entirely new window into what astronomers call galactic ecology, the study of how matter, energy, and potentially even biological materials flow between stellar systems across the galaxy. For decades, we imagined stellar systems as isolated islands separated by vast gulfs of empty space. Now we understand that these islands are connected by currents of interstellar debris, creating a dynamic galactic ecosystem where material constantly flows between stars. The implications for understanding how planetary systems form and evolve are profound. Traditional models of solar system formation assumed a closed system. The Sun and planets formed from a single collapsing molecular cloud, and the current inventory of material is simply what remained after planet formation. But if stellar systems regularly exchange material through interstellar visitors, then planetary systems might be more open than we thought, occasionally receiving inputs of matter from other systems. This exchange could have affected Earth's own history. In the early solar system, when the bombardment rate was much higher than today, interstellar objects might have delivered material to the young Earth. While the vast majority of impactors would have been native solar system debris, perhaps one in millions, or tens of millions, might have been interstellar. Over billions of years, these rare impacts could have introduced organic compounds, water, or even biological precursors from other stellar systems. The question of whether life could survive interstellar transfer remains hotly debated. Laboratory experiments have shown that some terrestrial organisms can survive exposure to space conditions for limited periods, but survival for millions of years in the harsh interstellar environment seems unlikely for most known life forms. However, the universe might harbour life forms more resilient than those on Earth, or life might find protection deep within interstellar objects where cosmic ray exposure is minimized. Even if biological transfer is unlikely, chemical transfer certainly occurs. Organic molecules form readily in interstellar space, in stellar atmospheres, and in planetary system debris disks. These molecules, frozen into cometary ices, could survive interstellar transfer intact. When interstellar comets impact planets or deposit material in planetary atmospheres during close approaches, they deliver these organic compounds to potentially habitable worlds. This organic matter could provide raw materials for the emergence of life, or supplement existing biochemistry with novel compounds. One of the most important questions raised by the discovery of 3 interstellar objects in 8 years is, how common are these visitors actually? The answer has profound implications for planetary defense, astrobiology, and our understanding of galactic structure and dynamics. Current estimates based on the detection rate and the observational biases of existing sky surveys suggest that at any given time, there might be thousands of interstellar objects within the orbit of Neptune. Most are small, dark, and inactive, making them effectively invisible to current detection methods. Only when they approach close enough to the Sun to heat up and begin outgassing if they contain volatiles do they become bright enough to detect. The size distribution of interstellar objects remains highly uncertain. We've detected 3 relatively large objects, ranging from hundreds of meters to potentially kilometers across. But for every large object, there are likely millions of smaller ones, ranging down to dust grain size. This size distribution matters enormously for understanding how much mass is actually flowing through our solar system in the form of interstellar debris. Some astronomers have proposed that interstellar objects might occasionally be captured by the Sun's gravity, becoming permanent members of our solar system. The capture mechanism would involve close encounters with Jupiter or other giant planets that slow the object enough for it to become gravitationally bound. Computer simulations suggest this might happen rarely, perhaps once every few million years, but over the solar system's 4.5 billion year history, it could have resulted in a substantial captured population. If some objects in the outer solar system are actually captured interstellar visitors, they would provide accessible targets for detailed study. Spacecraft missions to the outer solar system might visit captured interstellar objects without needing the extraordinary delta V required to intercept fast-moving visitors like 3I Atlas. Identifying which outer solar system objects might be captured interstellar visitors presents a significant observational challenge, as they would be difficult to distinguish from native Kuiper belt objects without detailed compositional or dynamical analysis. The study of 3I Atlas exemplifies modern astronomy's increasingly collaborative and democratic nature. Professional astronomers working at major observatories provide the bulk of detailed observations, but amateur astronomers, citizen scientists, and automated systems all contribute crucial data and discoveries. Amateur astronomer Gennady Borisov discovered 2I Borisov using a telescope he built himself, a remarkable achievement demonstrating that significant discoveries remain accessible to dedicated amateur observers with modern equipment. The Atlas system that discovered 3I Atlas represents another approach. Fully automated survey systems that scan the sky continuously, requiring human intervention only when interesting objects are detected. Citizen science projects allow members of the public to contribute to astronomical research by analyzing data, classifying objects, or searching for anomalies that automated algorithms might miss. Projects like Galaxy Zoo and Planet Hunters have demonstrated that crowdsourced analysis can achieve results comparable to professional astronomers, while engaging thousands of people in authentic scientific research. The study of interstellar objects benefits particularly from this global collaborative approach. These objects move quickly and are visible from Earth for limited periods, making time-domain observations crucial. A global network of observers can provide nearly continuous coverage, detecting short-lived events that might be missed if observations were limited to a few professional facilities. Amateur astronomers in different time zones provide redundant coverage, increasing confidence in measurements and catching transient phenomena. Social media and online communication platforms enable real-time coordination of observing campaigns. When an interesting event occurs, an outburst, a brightness anomaly, or unusual spectroscopic features, observers worldwide can be alerted within minutes and can redirect their instruments to capture data. This rapid response capability has become increasingly important as astronomy transitions towards studying transient phenomena that change on timescales of hours or days. As we await the results of 3I Atlas's perihelion passage, we can look forward to an exciting future for interstellar object science. Next-generation survey telescopes will detect these visitors earlier and more frequently, providing better opportunities for detailed study. The Vera C. Rubin Observatory, expected to begin operations soon, will revolutionize transient astronomy. Its large mirror and wide field of view will enable it to scan the entire visible sky every few nights, detecting objects much fainter than current surveys can observe. Simulations predict Rubin. Observatory might detect dozens of interstellar objects per year, transforming the field from studying rare visitors to building statistical samples that reveal population-wide patterns. Earlier detection enables better observation campaigns. If we can identify interstellar visitors while they're still beyond Jupiter's orbit, we'll have months or years to study them as they approach the Sun, rather than the weeks or days available for objects detected late. This extended baseline allows tracking of compositional changes as heating increases, measurement of rotation evolution, and detection of subtle activity beginning at large heliocentric distances. Space mission concepts for intercepting interstellar objects have been proposed by various space agencies and research groups. The technological challenges are formidable. Matching the high velocities of interstellar visitors requires enormous fuel expenditure, and the brief warning time makes mission preparation extremely difficult. However, several concepts appear feasible with current or near-term technology. One approach involves pre-positioning a spacecraft in the outer solar system equipped with a high-velocity interceptor module. When an interesting interstellar object is detected approaching the inner solar system, the interceptor would launch on a trajectory to rendezvous with the visitor, perhaps deploying impactors, sample return capsules, or landing probes. The spacecraft would need to be designed for long dormant periods in deep space followed by brief periods of intense activity. Another concept involves very rapid response missions launched from Earth once an interstellar object is detected. These missions would use high-energy trajectories and advanced propulsion systems to reach the visitor before it exits the inner solar system. The brief rendezvous time would limit scientific investigations to flyby observations, but even brief encounters could yield data impossible to obtain from Earth-based telescopes. More ambitious concepts involve developing standing capabilities, spacecraft, and infrastructure specifically designed for interstellar object studies, maintained in readiness for rapid deployment when targets are detected. This approach would be expensive, but could enable detailed investigations of multiple interstellar visitors over time, gradually building a comprehensive understanding of extrasolar matter. Regardless of what happens during perihelion, 3I Atlas has already taught us important lessons about the galaxy we inhabit and our place within it. The object's existence confirms that stellar systems throughout the galaxy produce and eject enormous quantities of debris, creating a pervasive background of interstellar objects. The extreme velocity and unusual trajectory alignment raise questions about ejection mechanisms and galactic dynamics that will drive theoretical research for years to come. The unprecedented chemical composition, particularly the extreme carbon dioxide enrichment, challenges our understanding of how comets form and evolve. Does 3I Atlas represent a common type of object that our solar system simply never produced? Or is it an outlier, an unusually carbon-rich object even among interstellar visitors? Only by detecting and characterizing many more interstellar comets can we answer these questions and understand the full diversity of planetary system formation conditions throughout the galaxy. The trajectory alignment remains perhaps the most intriguing mystery. With only 3 confirmed interstellar visitors, we can't yet determine whether 3I Atlas's ecliptic alignment is genuinely anomalous or simply a coincidence that will become commonplace as our sample size increases. If future interstellar visitors show similar alignments more frequently than random arrival would predict, it could indicate systematic effects we don't yet understand. Perhaps preferred ejection directions from stellar systems, or galactic structure that channels objects along certain trajectories. Some researchers have speculated about more exotic explanations. Could there be gravitational focusing effects from large-scale galactic structure, spiral arms, dark matter concentrations, or stellar streams that preferentially direct interstellar objects towards certain trajectories? Or might some interstellar objects be deliberately targeted, whether by natural processes we don't understand or artificial guidance systems? These ideas remain highly speculative, but they demonstrate how interstellar visitors challenge us to think in new ways about galactic dynamics and our cosmic environment. At its heart, the story of 3I Atlas is about human curiosity and our deep need to understand the universe around us. For millennia, humans have looked up at the night sky and wondered about the lights moving against the stellar background. Ancient astronomers tracked planets, the wandering stars, and tried to understand their motions. Comets were seen as omens, signs from the gods, harbingers of change. Now we understand these phenomena in physical rather than mystical terms, but the sense of wonder remains. When we discover that some visitors to our solar system come from other star systems, carrying matter processed by alien suns, that sense of wonder only deepens. We're no longer just observing our own planetary system. We're sampling the galaxy itself, studying matter that has journeyed across light years to reach us. This expanded perspective changes how we think about ourselves and our place in the cosmos. We are not isolated, living on a tiny world circling an ordinary star in an unremarkable part of the galaxy. We are participants in a vast galactic ecosystem, connected to other stellar systems by flows of matter and energy that span the Milky Way. The atoms in our bodies have cycled through multiple stars, travelled across interstellar space, and eventually assembled into the complex forms that support life and consciousness. 3i Atlas reminds us that the universe is stranger and more wonderful than we often remember in our daily lives. This icy visitor from another star system, racing through our cosmic neighbourhood at incomprehensible speeds, connects us to processes operating on timescales of billions of years and distance scales of light years. Yet we can study it, measure its properties, understand its composition, and predict its behaviour using physical laws we've discovered through careful observation and reasoning. This ability to understand cosmic phenomena, to take a point of light moving across the sky and deduce its origin, composition, trajectory, and fate, represents one of humanity's greatest achievements. It demonstrates that the universe is comprehensible, that natural laws operate consistently across vast distances, and that patient observation, combined with rigorous reasoning, can reveal nature's deeper secrets. Right now, as you're watching this video, something extraordinary is hurtling through our solar system at a mind-bending 130,000 miles per hour. It's moving faster than any visitor we've ever recorded, following a trajectory so extreme that it defies everything we thought we knew about celestial mechanics. This isn't just another space rock drifting through the cosmic void. This is 3i Atlas, the third confirmed interstellar object to grace our solar system, and it's about to reach a moment that could rewrite our understanding of what happens when alien matter meets our sun. Tonight, we're diving into one of the most anticipated astronomical events of our lifetime, a cosmic mystery that has astronomers around the world holding their breath as they watch an ancient traveller from the depths of space approach its closest encounter with our star. Before we embark on this journey to the edge of known physics, I'd love to know where you're watching from and what keeps you staring up at the night sky, wondering about our place in this vast universe. And if you find yourself drawn to these cosmic mysteries that challenge everything we think we know, I'd be grateful if you gave this video a like and perhaps subscribe to join our community of space explorers. As 3i Atlas continues its relentless approach toward the sun, it's giving us an unprecedented opportunity to study how interstellar matter behaves under the influence of stellar radiation. The James Webb Space Telescope has already provided stunning insights into the comet's composition, revealing a chemistry unlike anything we've seen before. The near-infrared spectroscopy data shows that 3i Atlas is unusually rich in carbon dioxide, with a CO2 to water ratio of 7.6 to 1, the highest ever observed in any comet. For context, most solar system comets show roughly equal amounts of water and carbon dioxide, or often have water dominating by factors of 2 to 10. The extremely high carbon dioxide content in 3i Atlas suggests fundamentally different formation conditions. In our solar system, water ice dominates in the outer regions because water has a higher sublimation temperature than carbon dioxide. The snow line or frost line in our protoplanetary disk formed at around 3 to 5 astronomical units from the Sun, while the carbon dioxide ice line formed much farther out. This chemical signature raises profound questions about the environmental conditions in the alien star system where 3i Atlas formed billions of years ago. The abundance of carbon dioxide could indicate several possibilities. The object might have formed in the outer reaches of its parent system, beyond the carbon dioxide ice line, where temperatures were cold enough for CO2 to freeze before water ice became dominant. Alternatively, the parent star might have been cooler than our Sun, pushing the ice lines closer in and creating different zones of chemical composition. Another possibility involves cosmic ray processing. During its millions or billions of years, drifting through interstellar space, 3I Atlas would have been subjected to intense bombardment by cosmic rays, high-energy particles that can alter surface chemistry. These rays could have preferentially destroyed water ice while leaving carbon dioxide intact, or triggered chemical reactions that produced more carbon dioxide from organic compounds. The object's surface might have been gradually transformed during its cosmic journey, giving us a window into the harsh conditions of interstellar space. The spectroscopic data also revealed trace amounts of other compounds that provide clues to the object's history. Carbon monoxide, detected at lower concentrations, suggests the presence of highly volatile ices that have survived the journey through interstellar space. Carbonyl sulfide, a more complex molecule, indicates that the object contains sulfur compounds formed through processes we're still working to understand. Each molecular signature adds another piece to the puzzle of where 3I Atlas came from and what it experienced during its journey. The physical characteristics of 3I Atlas remain tantalizingly uncertain, highlighting the challenges of studying objects at interstellar distances. Hubble Space Telescope observations suggest the nucleus diameter falls somewhere between 440 meters and 5.6 kilometers, but the presence of an active coma makes precise measurements challenging. The coma, the cloud of gas and dust surrounding the nucleus, scatters and reflects sunlight, making it difficult to isolate the solid nucleus at the center. This wide uncertainty range creates challenges for theoretical predictions. A 440-meter nucleus would have a volume roughly equivalent to a large mountain, while a 5.6-kilometer nucleus would be comparable to a small city. The difference in mass between these extremes could be a factor of 1,000 or more, dramatically affecting how the object responds to solar heating and tidal forces. Recent estimates from Harvard astrophysicist Avi Loeb suggest the object could be far more massive than initially thought, with a possible mass exceeding 33 billion tons. If accurate, this would make 3I Atlas significantly more substantial than either of our previous interstellar visitors. Oumuamua, estimated to be roughly 400 meters long, likely had a mass of millions of tons. 2I Borisov, with a nucleus perhaps a kilometer across, probably weighed billions of tons. A 33 billion ton 3I Atlas would represent a substantial chunk of interstellar debris. The mass estimate comes from analyzing the comet's brightness, outgassing rate, and how its trajectory changed due to non-gravitational forces like sublimation. However, these calculations depend on assumptions about the object's density, albedo, reflectivity, and internal structure, all of which remain highly uncertain. Is the nucleus a solid chunk of ice and rock, or a loosely bound rubble pile? Is it relatively pure ice, or does it contain a high fraction of rocky material? Different assumptions lead to wildly different mass estimates. This uncertainty in mass and size has profound implications for what we might expect during perihelion. A larger, more massive object would respond differently to solar heating than a smaller, more fragile one. The thermal stresses induced by rapidly increasing solar radiation could trigger spectacular outgassing events, structural changes, or even complete fragmentation depending on the object's internal composition and structural integrity. A massive, solid nucleus might sail through perihelion relatively unchanged, while a smaller fragile object could be torn apart by thermal stress and tidal forces. Currently, 3I Atlas is demonstrating typical cometary behavior as it approaches the inner solar system. The sun's heat and radiation are bringing the comet to life, causing it to release gas and dust that collects in a luminous halo surrounding the nucleus. As of early October 2025, JWST observations show the nucleus is actively sublimating, releasing 129 kilograms of carbon dioxide per second, along with smaller amounts of water vapor, carbon monoxide, and carbonyl sulfide. To put this outgassing rate in perspective, 3I Atlas is currently losing mass at a rate of roughly 11 tons per day, equivalent to a large truck's worth of material evaporating into space every 24 hours. As the comet approaches perihelion, this rate will increase exponentially. By the time it reaches its closest approach to the Sun, the outgassing rate could be hundreds or thousands of times higher, potentially reaching tons per second. This outgassing creates the characteristic coma that makes the comet visible to our telescopes, but it also represents a fundamental transformation of the object itself. Every second that passes, 3I Atlas is literally evaporating into space, shedding the frozen record of its ancient origins into the solar wind. The material being released carries isotopic signatures and molecular structures that encode information about stellar nucleosynthesis processes in alien suns, interstellar chemistry, and the physical conditions that existed during the formation of distant planetary systems. The coma around 3I Atlas has been growing steadily as the comet approaches the Sun. Current observations show the coma extending roughly 100,000 kilometers from the nucleus, large enough to swallow Earth. As sublimation rates increase, this coma could expand to millions of kilometers, though the material becomes increasingly tenuous as it spreads out. If conditions are right, 3I Atlas might develop visible dust and gas tails that could extend tens of millions of kilometers behind the comet. The dust component of the coma provides additional clues about the nucleus's composition. Spectroscopic analysis of the dust particles reveals silicate minerals and organic compounds that survived the formation of the parent planetary system and the subsequent journey through interstellar space. Some of these particles might be older than our solar system, formed in the atmospheres of stars that died before our Sun was born. Each dust grain is a tiny time capsule carrying information about cosmic processes that occurred billions of years ago. The comet's journey through our solar system has already provided one spectacular observational opportunity. On October 3rd, 2025, 3I Atlas passed within 30 million kilometers of Mars, offering European Space Agency orbiters and NASA missions at the Red Planet their closest view of an interstellar visitor. Both Mars Express and the ExoMars Trace gas orbiter turned their sophisticated instruments toward the ancient wanderer, capturing images and spectroscopic data that will help refine our understanding of its composition and behavior. The geometry of this encounter was particularly favorable. From Mars's perspective, 3I Atlas passed nearly overhead, allowing spacecraft in Martian orbit to observe the comet without the interference of Mars's atmosphere or the geometric constraints that often limit Earth-based observations. The ExoMars Trace gas orbiter, designed to study the Martian atmosphere with extreme sensitivity, was able to detect trace gases in 3I Atlas's coma at concentrations that would be impossible to measure from Earth. Mars Express, equipped with high-resolution imaging cameras, captured detailed photographs of the comet's nucleus and inner coma. These images revealed structure in the coma that suggests non-uniform outgassing, with jets of material erupting from specific locations on the nucleus's surface. This asymmetric activity indicates that the nucleus has regions with different compositions or thermal properties, possibly reflecting its layered internal structure or varying degrees of weathering during its interstellar journey. This Mars encounter represents more than just a photographic opportunity. The gravitational influence of Mars, while minimal compared to the Sun's overwhelming pull, still provides astronomers with precise measurements of 3I Atlas's trajectory and mass. By carefully tracking how the comet's path was perturbed by Mars's gravity, researchers can constrain estimates of the object's mass, one of the key unknowns that affects all predictions about its behavior during perihelion. What the Mars observations revealed is that 3I Atlas is behaving like a comet in some respects, while defying conventional cometary physics in others. The active sublimation creating its visible coma follows predictable thermodynamic principles, but the chemical composition and mass estimates continue to challenge our theoretical models. The object appears to be simultaneously familiar and alien, conforming to our understanding of icy bodies, while exhibiting characteristics we've never encountered before. The data from Mars also provided unexpected insights into the comet's rotation state. By watching how brightness varied over several hours as different parts of the nucleus rotated into and out of sunlight, astronomers determined that 3I Atlas is spinning with a period of roughly 12 hours. This rotation rate is relatively slow for a small body, suggesting either a relatively large nucleus or some mechanism that has damped the rotation over time. The rotation appears to be complex, possibly tumbling rather than spinning around a single axis, which could indicate a non-spherical or structurally heterogeneous nucleus. But the most dramatic chapter of 3I Atlas's story is yet to unfold. On October 29th, 2025, this interstellar wanderer will reach its perihelion, closest approach to the Sun, at a distance of 1 astronomical unit, 0.36 astronomical units. This places the encounter roughly midway between Earth and Mars, in a region where solar radiation intensity increases dramatically and the physics of sublimation and thermal stress reach extreme levels. To understand what's at stake, consider that at Earth's distance of 1 astronomical unit, the Sun delivers about 1 kilowatt of power per square meter, roughly equivalent to a space heater. At 3I Atlas's perihelion distance of 1.36 astronomical units, the solar energy flux is about 54% of Earth's value, or roughly 540 watts per square meter. While this might not sound extreme compared to conditions near the Sun's surface, it represents an enormous increase compared to the near-zero background radiation the comet experienced during its interstellar journey. The perihelion passage represents a cosmic crucible where the ancient ice and rock of another star system will be tested against the full power of our Sun. At this distance, solar radiation will deposit gigawatts of energy onto 3I Atlas's surface, driving sublimation rates to potentially explosive levels. The temperature differential between the sunlit and shadowed sides of the nucleus could create thermal stresses capable of fracturing the object along pre-existing fault lines or structural weaknesses. Consider what happens when frozen carbon dioxide, the dominant component of 3I Atlas's coma, begins sublimating at accelerating rates during perihelion approach. Carbon dioxide ice sublimates at temperatures around 195 Kelvin, -78 degrees Celsius, at typical cometary pressures. As the sunlit surface of 3I Atlas heats up, regions rich in carbon dioxide will begin outgassing vigorously, creating internal pressure that must escape through pores and fractures in the nucleus. The phase transition from solid to gas occurs with tremendous efficiency in the vacuum of space, but it also creates internal pressure gradients that can fracture the nucleus along structural weaknesses. Every cubic meter of carbon dioxide ice that sublimates produces hundreds of cubic meters of gas that must escape through the object's surface. This gas flow creates forces that push outward on the surrounding material, potentially widening existing fractures or creating new ones. In extreme cases, the pressure can exceed the tensile strength of the material, causing explosive fragmentation events. The thermal environment during perihelion passage will subject 3I Atlas to temperature differentials unlike anything it has experienced during its interstellar journey. The side facing the Sun could heat up to temperatures approaching 200 Kelvin or higher in areas with low albedo, while the shadowed hemisphere remains at temperatures below 100 Kelvin. This 100-degree temperature difference creates thermal stress patterns that propagate through the object's interior like seismic waves. Thermal stress arises because materials expand when heated and contract when cooled. When different parts of an object are at different temperatures, they want to expand or contract by different amounts, creating internal forces that can fracture solid materials. rock is particularly susceptible to thermal stress fracturing, while ice has some capacity to deform plastically at these temperatures. However, a nucleus composed of both ice and rock, as most comets are, will experience complex stress patterns as these different materials respond differently to temperature changes. But thermal stress represents only one component of the complex physics operating during perihelion passage. Tidal forces from the Sun's gravity, while much weaker than those that destroyed comet Shoemaker-Levy 9 at Jupiter, could still play a role in determining 3I Atlas's fate. The differential gravitational pull across the object's extent creates forces that tend to stretch it along the Sun-comet line, while compressing it perpendicular to that axis. The tidal force can be calculated using the formula that depends on the mass of the Sun, the distance to 3I Atlas, and the size of the nucleus. For an object the size of 3I Atlas at its perihelion distance, the tidal forces are relatively small, measured in fractions of a Pascal, but they act continuously and uniformly across the entire body. For a loosely bound rubble pile, or an object with pre-existing structural weaknesses, these modest forces could be the final straw that triggers catastrophic disintegration. Spin dynamics add another layer of complexity, as asymmetric sublimation creates thrust forces that act like tiny rocket engines across the object's surface. These forces can alter its rotation rate in unpredictable ways. This is exactly what happened with Oumuamua. Its mysterious acceleration was likely due to asymmetric outgassing creating a net thrust. But while Oumuamua experienced a gentle push that slightly modified its trajectory, 3I Atlas could experience more dramatic effects. Many comets experience spin-up during close solar encounters, rotating faster and faster until centrifugal forces overcome the weak gravity holding their loosely bound materials together. The critical rotation rate depends on the nucleus's density and structural strength. For a typical comet nucleus with density around 500 kilograms per cubic meter, rotation periods shorter than a few hours can generate centrifugal forces that exceed gravitational binding. If 3I Atlas's rotation speeds up from its current 12-hour period to just a few hours, centrifugal effects could tear it apart. The extreme velocity of 3I Atlas also creates unique physical challenges during perihelion. The object will be moving at approximately 68 kilometers per second at its closest solar approach, subjecting it to intense aerodynamic pressures from the solar wind and interplanetary medium. While space is essentially a vacuum, at such extreme speeds even the tenuous particle density of the inner solar system can exert measurable forces. The solar wind, a stream of charged particles flowing outward from the Sun, has a typical density of about 5 particles per cubic centimeter at Earth's orbit, and somewhat higher closer to the Sun. At 3I Atlas's velocity of 68 kilometers per second, it's moving roughly 3 times faster than the solar wind itself, creating a bow shock where the comet plows through the solar wind plasma. The ram pressure from this interaction is small but non-zero, potentially contributing to erosion of the coma or even the nucleus surface. Additionally, the electromagnetic environment near the Sun becomes increasingly hostile. Solar magnetic fields, particle radiation, and intense electromagnetic flux create conditions that could interact with any magnetic or electrical properties of the comet's nucleus. While comets are generally non-magnetic, the interaction between the solar wind and the ionized gas in the coma creates complex electromagnetic structures that can affect the coma's shape and evolution. Historical precedent suggests several possible outcomes for this solar encounter, though 3I Atlas's interstellar origin adds uncertainty to all predictions. Natural comets approaching the Sun often experience dramatic increases in brightness as sublimation rates accelerate, creating spectacular tails that can stretch for millions of kilometers. The Great Comet of 1844, which passed within just 0.5 astronomical units of the Sun, became visible in broad daylight and developed a tail that spanned half the sky. If 3I Atlas responds similarly to increased solar heating, it could put on a spectacular show for observers. However, not all comets survive their solar encounters intact. The famous case of Comet Shoemaker-Levy 9 provides a dramatic example of tidal disruption, though that event involved Jupiter's gravity rather than the Sun's. When that comet passed within Jupiter's Roche limit, the distance at which tidal forces exceed an object's self-gravity, in 1992, tidal forces tore it apart into at least 21 fragments that later crashed into Jupiter's atmosphere in one of the most spectacular astronomical events ever witnessed. The Roche limit depends on the densities of both the massive body and the smaller object, as well as the smaller object's structural strength. For a rubble pile comet with minimal internal strength, the Roche limit for the Sun would be around 1.4 solar radii, or about 0.01 AU. 3I Atlas will pass nowhere near this close, so pure tidal disruption is unlikely. However, the combination of tidal forces, thermal stress, and rotational stress could create conditions that weaken the nucleus enough for it to break apart. More recently, comet ISON disappeared entirely during its 2013 perihelion passage, likely disintegrating completely due to thermal and tidal stresses. ISON passed within just 0.01 astronomical unit of the Sun's surface, experiencing temperatures exceeding 2000 Kelvin and tidal forces millions of times stronger than 3I Atlas will experience. The comet brightened dramatically as it approached the Sun, then faded rapidly and fragmented as it rounded perihelion. Post-perihelion observations detected only a diffuse cloud of debris, suggesting the nucleus had been completely destroyed. Conversely, many comets survive multiple perihelion passages with relatively minor changes. Halley's Comet has been orbiting the Sun for thousands of years, passing within 0.6 astronomical units every 76 years. Each passage strips away a surface layer several meters thick, but the nucleus, estimated at 15 kilometers in diameter, contains enough material to survive many more orbits. Similarly, Comet Encke, with a perihelion distance of just 0.33 astronomical units, has been observed for over 200 years and completes an orbit every 3.3 years, yet continues to survive and produce gas and dust. The determining factors include the object's size, composition, internal structure, and the specific details of its solar encounter geometry. Large, solid nuclei with high rock content tend to survive better than small, volatile, rich objects. Slow rotators maintain structural integrity better than fast spinners, objects that approach gradually, allowing their surfaces to thermally equilibrate, fare better than those that plunge rapidly toward the Sun. Yet there's another possibility that keeps some researchers awake at night, staring at data that doesn't quite fit conventional models. What if 3I Atlas isn't entirely natural? The object's unusual properties, extreme velocity, peculiar trajectory alignment, and unprecedented chemical composition, have led some scientists to consider whether we might be observing humanity's first encounter with technology from another civilization. This isn't science fiction speculation, but serious scientific consideration based on observational anomalies. Harvard's Avi Loeb has argued that certain characteristics of interstellar visitors, including the famous acceleration exhibited by Oumuamua, could potentially be explained by artificial origins. Oumuamua's acceleration couldn't be easily explained by conventional outgassing because no coma or dust tail was detected. Yet the object accelerated away from the Sun as if pushed by rocket thrust. Loeb and his colleagues proposed that Oumuamua might have been a light sail, a thin reflective sheet pushed by solar radiation pressure. The acceleration observed was consistent with what you'd expect from a sail, with thickness measured in fractions of a millimeter and area to mass ratio hundreds of times larger than any natural object. While natural explanations involving exotic hydrogen icebergs or nitrogen ice remain possible, the light sail hypothesis has not been definitively ruled out. 3I Atlas presents its own set of puzzling characteristics that, while different from Oumuamua's, raise similar questions. The statistical improbability of its trajectory alignment, less than 0.2% chance for a random interstellar object, suggests either extraordinary coincidence or some form of targeting. If an advanced civilization wanted to send a probe to investigate our solar system, arriving along the ecliptic plane would be a logical choice, as it would allow close approaches to all the major planets. The extreme velocity is another potential indicator. While natural gravitational slingshot effects can accelerate objects to high speeds, doing so while maintaining a specific trajectory alignment is extraordinarily difficult. It's like trying to throw a dart at a bullseye while riding a roller coaster. Possible in principle, but requiring either incredible luck or some form of guidance system. If 3I Atlas were artificial, its behavior during perihelion might deviate from natural comet expectations in detectable ways. Artificial materials could have different thermal properties, structural responses, or even active systems that become operational when exposed to stellar radiation. The perihelion passage would represent not just a test of natural physics, but potentially the activation or revelation of technologies designed by minds that evolved under alien stars. What might an interstellar probe look like? It would need to survive millions of years in the harsh environment of interstellar space, withstanding cosmic ray bombardment, micrometeorite impacts, and the extreme cold of deep space. A thick outer shell of ice would provide excellent radiation shielding and micrometeorite protection, while allowing the probe to masquerade as a natural comet when it entered a target stellar system. The unusually high carbon dioxide content could be intentional, designed to create a bright coma that makes the object easy to detect and track. The probe might contain instruments dormant during the interstellar journey, but designed to activate when exposed to stellar radiation. Solar panels could unfold, batteries could recharge, and communication systems could begin transmitting data back toward the home system. From our perspective, we might observe anomalous behavior, unexpected changes in brightness, trajectory modifications that can't be explained by outgassing, or even electromagnetic emissions at frequencies unusual for natural objects. However, it's crucial to maintain scientific skepticism. Extraordinary claims require extraordinary evidence, and so far, all of 3I Atlas's observed properties can be explained, albeit sometimes awkwardly, by natural processes. The high carbon dioxide content might reflect unusual formation conditions. The precise trajectory alignment might be remarkable coincidence. The extreme velocity might result from a particularly violent ejection event, followed by favorable gravitational encounters during its journey. The scientific method demands that we consider the artificial origin hypothesis seriously enough to look for evidence that could confirm or refute it, while recognizing that natural explanations remain more plausible until proven otherwise. If 3I Atlas does exhibit behavior during perihelion that cannot be explained by conventional cometary physics, it would justify more serious consideration of non-natural origins. Until then, we should assume it's natural, while remaining alert for anomalies. The timing of 3I Atlas's perihelion creates a particularly cruel irony for Earth-based observers. The comet will reach its closest solar approach on October 29th, 2025, but solar conjunction will place it on the opposite side of the Sun from Earth's perspective. This means the most dramatic phase of the encounter will occur when direct observation from our planet is impossible, hidden behind the brilliant disk of our star. Solar conjunction creates multiple challenges for observation. First and most obviously, the Sun's overwhelming brightness makes it impossible to observe anything near it without specialized equipment and techniques. Even with coronagraphs, instruments designed to block the Sun's direct light, observing objects within a few degrees of the Sun is extremely difficult from Earth's surface. The scattered sunlight in Earth's atmosphere creates a bright background that overwhelms the faint signals from comets. Second, the geometric configuration places 3i Atlas nearly along the Earth-Sun line, meaning we're viewing it from nearly behind the Sun. This is the worst possible viewing angle for observing cometary activity, as any dust tail would be pointing away from us and we'd be looking primarily at the shadowed side of the nucleus. It's like trying to observe a campfire while standing directly behind a spotlight. The glare overwhelms the signal you're trying to detect. This observational blackout period extends from mid-October through early November, encompassing not just perihelion but the crucial weeks when thermal effects, outgassing changes, and potential structural modifications would be most apparent. It's as if the universe has conspired to hide the most interesting part of the story behind a cosmic curtain, leaving us to piece together what happened from before and after observations. However, this isn't a complete scientific loss. Space-based observatories positioned at different points in the solar system can potentially maintain some observational coverage during Earth's solar conjunction period. The Parker Solar Probe, currently making its own close approaches to the Sun, might be positioned to observe 3i Atlas during perihelion, though the extreme solar environment creates its own observational challenges. Parker Solar Probe was designed to study the Sun's corona from closer than any previous spacecraft, with a perihelion distance of just 0.046 AU, about 9.86 solar radii. The spacecraft carries instruments designed to operate in the intense radiation environment near the Sun, including cameras that could potentially image 3i Atlas if the geometry is favourable. The probe's wide-field imager for Solar Probe, WISPR, has already captured images of several comets and the zodiacal light, demonstrating its capability for observing faint objects near the Sun. The European Space Agency's Solar Orbiter represents another potential observer. This spacecraft, launched in 2020 to study the Sun's polar regions and solar wind, travels in an elliptical orbit that brings it as close as 0.3 astronomical units to the Sun. Depending on its orbital position, in late October 2025, Solar Orbiter might have a favourable viewing angle for observing 3i Atlas during perihelion. The spacecraft carries imaging instruments and spectrographs that could provide unique data about the comet's response to intense solar heating. Additional ground-based observations might be possible from high-altitude observatories during twilight hours in the days immediately before and after perihelion. Skilled observers using specialized equipment can sometimes detect bright comets very close to the Sun during the brief windows, when the Sun is below the horizon, but the comet is still above it. This requires careful timing, clear skies, and typically access to large telescopes at mountaintop observatories far from urban light pollution. The data collected before and after solar conjunction will tell a story written in spectral lines and brightness measurements. If 3i Atlas emerges from perihelion with dramatically altered characteristics, sudden increases in brightness, changes in coma color or structure, or new spectroscopic signatures, it will provide crucial insights into how interstellar matter responds to stellar processing. Conversely, if the object appears unchanged or fails to emerge at all, it would suggest either complete disintegration or behavior patterns that challenge our current understanding of cometary physics. The scientific significance of 3i Atlas extends far beyond academic curiosity about interstellar visitors. This object represents a natural experiment in planetary defense, demonstrating how our solar system responds to high-velocity interstellar impactors. While 3i Atlas poses no threat to Earth, understanding the physical processes that govern such encounters is crucial for assessing the long-term risks posed by similar objects that might pose actual collision threats. Current planetary defense strategies focus almost entirely on asteroids and comets native to our solar system, which approach Earth at typical velocities of 15 to 30 kilometers per second. An interstellar impactor traveling at 60 kilometers per second would carry roughly 4 times the kinetic energy at the same mass, making it potentially far more destructive. Moreover, the high approach velocities and unusual trajectories of interstellar objects might give us less warning time than we'd have for native solar system threats. The study of interstellar visitors also provides unique insights into stellar system formation and evolution processes occurring throughout the galaxy. Every molecule released from 3I Atlas's nucleus carries isotopic signatures that encode information about nucleosynthesis in its parent star, chemical processes in its birth nebula, and the radiation environment of its home system. These cosmic fossils provide direct samples of matter processed by alien stars, offering glimpses into the diversity of planetary system formation across galactic distances. Isotope ratios are particularly revealing. Different stellar masses and evolutionary stages produce different ratios of isotopes through nucleosynthesis. By measuring the ratios of oxygen-16 to oxygen-18, carbon-12 to carbon-13, and nitrogen-14 to nitrogen-15 in material released from 3I Atlas, astronomers can infer properties of the star around which it formed. Did the parent star have higher or lower metallicity than our Sun? Was it more or less massive? These questions can be addressed through careful isotopic analysis. The implications for astrobiology and the search for extraterrestrial intelligence cannot be overlooked. If interstellar objects prove more common than previously thought, they represent potential vectors for transporting organic compounds or even biological materials between stellar systems, a hypothesis known as panspermia. The chemical complexity observed in 3I Atlas's coma, with its carbon dioxide, carbon monoxide, and organic sulfur compounds, suggests that interstellar space may harbour richer molecular inventories than we realised. Panspermia, first proposed in the late 19th century, suggests that life might spread between planets or even star systems via comets, asteroids, or interstellar objects. While most scientists consider this hypothesis unlikely for interstellar distances, the journey times are too long and radiation exposure too intense for most known organisms to survive, the discovery that interstellar objects regularly visit our solar system reopens the question. Could hardy microorganisms, protected deep within an icy nucleus, survive the millions of years required for interstellar transfer? Laboratory studies have shown that some terrestrial microorganisms, particularly extremophiles like tardigrades and certain bacteria, can survive exposure to space conditions for extended periods. Some can withstand temperatures near absolute zero, intense radiation, and complete desiccation. While survival for millions of years remains speculative, the existence of interstellar transport mechanisms makes biological transfer between stellar systems at least theoretically possible. Think about the extraordinary journey that brought this ancient wanderer to our cosmic doorstep. Somewhere in the galaxy, perhaps dozens or even hundreds of light years from where you're sitting right now, 3I Atlas began its existence in the swirling disk of matter surrounding a young star. The processes that shaped its formation occurred under conditions we can only imagine, influenced by stellar radiation, gravitational dynamics, and chemical environments that may have been radically different from those that created our familiar solar system neighbours. Protoplanetary disks, the birthplaces of planets and smaller bodies, vary considerably from system to system. The composition depends on the parent star's metallicity, which determines how much carbon, oxygen, silicon, and other heavy elements are available to form solid materials. The disk's structure depends on the star's mass and luminosity, which determine where different materials can condense into solid form. The dynamics depend on whether the system has one star or multiple stars, and whether giant planets form early enough to perturb the distribution of smaller bodies. In our solar system, the giant planets, particularly Jupiter, played a crucial role in shaping the distribution of smaller bodies. Jupiter's powerful gravity scattered countless objects throughout the system, sending some crashing into the inner planets, others into the outer solar system to become Kuiper belt objects, and still others on escape trajectories that ejected them into interstellar space. Computer simulations suggest that for every planet that formed in our solar system, hundreds or thousands of planet-sized masses of smaller debris were ejected. The gravitational choreography required to launch 3I Atlas on its interstellar trajectory represents one of the most violent processes in planetary system evolution. To achieve its current velocity of 60 kilometers per second relative to our Sun, this object needed to experience gravitational encounters of extraordinary intensity. The most efficient mechanism is a close encounter with a massive planet. The more massive the planet, and the closer the approach, the more energy can be transferred. Binary star systems provide an alternative mechanism for ejecting material at high velocities. When two stars orbit each other closely, objects passing between them can experience gravitational boosts from both stars in sequence, potentially reaching very high velocities. In some cases, objects can be ejected entirely from the system when one star passes energy to the object, which then interacts with the second star before escaping. This gravitational juggling can produce ejection velocities higher than either star alone could achieve. During its millions or billions of years drifting through interstellar space, 3I Atlas experienced conditions that no object in our solar system has ever encountered. The interstellar medium, while nearly empty by terrestrial standards, contains trace amounts of gas, dust, and high-energy particles that slowly interact with any object passing through it. The typical density is about 1 atom per cubic centimetre, billions of times less dense than Earth's atmosphere at sea level, but still enough to cause measurable effects over millions of years. Cosmic rays, the most energetic particles in the galaxy, continuously bombarded the comet's surface, creating chemical changes and structural modifications that we're only beginning to understand. These particles, primarily protons and atomic nuclei, accelerated to near light speed by supernova remnants and other violent cosmic events, can penetrate meters into solid ice and rock. Each impact creates a cascade of secondary particles and chemical reactions, gradually altering the surface composition and creating new compounds not present in the original material. The temperature environment of deep space also left its mark on 3I Atlas. Far from any star's warming influence, the object's surface temperature would have stabilized at just a few degrees above absolute zero, around 3 Kelvin, set by the cosmic microwave background radiation left over from the Big Bang. At these temperatures, even the most volatile materials become frozen solid, creating conditions where chemical reactions essentially stop, and the object is preserved in a deep freeze for eons. This preservation is what makes interstellar objects so scientifically valuable. Unlike objects that remained in our solar system, continuously processed by solar radiation and collisions with other debris, interstellar wanderers, like 3I Atlas, spent most of their existence in cold storage, maintaining a relatively pristine record of their birth conditions. The surface may have been modified by cosmic ray exposure, but the interior likely remains largely unchanged from its formation billions of years ago. When we compare 3I Atlas to our previous interstellar visitors, the differences become even more intriguing, revealing the diversity of objects travelling between star systems. Oumuamua, discovered on October 19, 2017 by the Pan-STARRS telescope in Hawaii, was the first confirmed interstellar object. Its discovery fundamentally changed our understanding of what travels through the space between stars. Oumuamua exhibited several puzzling characteristics that still generate debate. Its elongated shape, estimated at roughly 400 by 40 meters based on brightness variations, was unlike any asteroid or comet previously observed. The object tumbled chaotically through space, completing a rotation every 7 to 8 hours, creating dramatic brightness variations as different surfaces reflected sunlight. Most mysteriously, careful tracking of its trajectory revealed a small but significant acceleration away from the Sun that couldn't be explained by gravitational forces alone. The acceleration was subtle, just a few millimeters per second squared, but persistent and measurable. For natural comets, such acceleration is typically caused by the rocket effect of sublimating gases, but Oumuamua showed no detectable coma, no dust tail, and no spectroscopic evidence of outgassing. Various natural explanations have been proposed. Perhaps it was outgassing pure hydrogen, which would be invisible to most detection methods. Perhaps it was made of unusually reflective material that created strong radiation pressure. Perhaps it had a highly unusual shape that concentrated outgassing effects. None of these explanations is entirely satisfying. Avi Loeb's light sail hypothesis suggested that Oumuamua might be a thin artificial structure, perhaps damaged or defunct, pushed by solar radiation pressure. The required geometry, a sail less than a millimeter thick with dimensions of hundreds of meters, would produce exactly the observed acceleration. While most astronomers favor natural explanations, the artificial hypothesis hasn't been definitively ruled out, and Oumuamua's true nature remains a mystery as it recedes into the depths of space, now too faint to observe. 2I Borisov, discovered on August 30th, 2019, by amateur astronomer Gennady Borisov using a home-built telescope, appeared more conventionally comet-like in its behavior and composition. It exhibited a clear coma and tail, developed an obvious dust tail as it approached the Sun, and showed spectroscopic signatures that matched expectations for icy bodies from the outer regions of planetary systems. The object's composition was similar to solar system comets, with water ice and carbon monoxide detected in ratios that seemed familiar. Borisov's nucleus was estimated at roughly 1 kilometer in diameter, making it substantially larger than Oumuamua. It approached the Sun to within 2 astronomical units, relatively distant by cometary standards, and was observed for several months before and after perihelion. The wealth of observational data confirmed that interstellar comets could behave according to familiar physical principles, providing a reassuring counterpoint to Oumuamua's mysteries. However, detailed analysis revealed some intriguing differences from solar system comets. Borisov's coma had unusual concentrations of carbon monoxide, higher than typical for solar system comets, and suggesting formation at very low temperatures. The dust properties also appeared somewhat different, with particles showing different scattering properties than typical solar system cometary dust. These subtle differences hinted that even normal interstellar comets form under conditions distinct from our solar system's environment. 3I Atlas occupies a unique position among these 3 visitors. It exhibits clear cometary activity with well-developed coma and active gas production, but its chemical composition, extreme velocity, and trajectory alignment differ markedly from both solar system comets and 2I Borisov. The unprecedented carbon dioxide to water ratio suggests formation conditions we haven't encountered before, while its extreme velocity indicates a particularly violent ejection or fortunate series of gravitational assists during its journey. The object appears simultaneously familiar and alien, conforming to some expectations while defying others in ways that could revolutionize our understanding of matter that originates beyond our solar system. Unlike Oumuamua, it shows clear evidence of volatiles and behaves like a comet. Unlike Borisov, its composition is highly unusual, and its trajectory remarkably well aligned with our solar system's architecture. It's as if each interstellar visitor brings its own set of puzzles for us to solve. The potential outcomes for 3I Atlas during its October 29th perihelion encounter span a remarkable range of possibilities, each carrying different implications for our understanding of how alien matter responds to stellar heating. Let's explore these scenarios in detail, from the most optimistic to the most catastrophic. The most scientifically valuable scenario involves 3I Atlas surviving largely intact while undergoing dramatic transformations that reveal its internal structure and composition. In this outcome, the comet would emerge from perihelion with its nucleus structurally sound, but with significantly increased outgassing and brightness. As it approaches perihelion, sublimation rates would increase exponentially, potentially reaching tons per second of material loss. The coma would expand dramatically, possibly to millions of kilometers in diameter. Dust entrained in the outflowing gas would form visible tails, a gas tail pointing directly away from the sun due to pressure from solar wind, and a curved dust tail following the comet's orbital path. From Earth, post-conjunction observers might see a dramatically brightened object with spectacular tail structures. Spectroscopic observations after perihelion would be crucial. If deeper, more pristine material from the nucleus interior becomes exposed due to surface erosion, we might detect compositional changes, perhaps lower carbon dioxide ratios in newly exposed material, or isotopic signatures different from the weathered surface. These changes would provide insights into how the object's composition varies with depth, revealing its layered internal structure. This scenario would also allow precise measurement of how much mass the comet lost during perihelion. By comparing pre- and post-perihelion brightness, coma size, and outgassing rates, astronomers could estimate the thickness of material stripped away. For a comet passing at 1.36 astronomical units, typical erosion might be a few meters of surface material, but the actual amount depends on composition, thermal properties, and nucleus rotation. A more dramatic possibility involves significant structural modifications during perihelion passage, with thermal stresses, tidal forces, or spin-up effects causing the nucleus to fragment into multiple pieces. This fragmentation could occur in several ways, each producing different observational signatures. Gradual splitting would involve the nucleus slowly separating into two or more large pieces over days or weeks. This typically happens when thermal stress opens a crack through the nucleus, and outgassing pressure gradually widens the crack until the pieces separate. The fragments would initially remain close together, each developing its own coma as they gradually diverge along slightly different trajectories. Observers would see an elongated or multiple-chord coma structure, eventually resolving into separate comets. Explosive fragmentation would be more dramatic, with the nucleus suddenly breaking apart into dozens or hundreds of pieces. This could occur if internal pressure from rapid sublimation exceeds the structural strength of confining material, essentially causing the nucleus to explode. The result would be a rapidly expanding cloud of fragments, each leaving a luminous trail as it releases gas and dust. Such events have been observed in solar system comets and create some of the most spectacular celestial displays. Tidal splitting, while less likely at 3I Atlas's perihelion distance, could occur if the nucleus has minimal structural strength. The differential gravitational pull would gradually stretch the nucleus until it separates into a string of fragments, similar to what happened to Comet Shoemaker-Levy 9 at Jupiter. The fragments would remain roughly aligned along the Sun-Comet line, creating a distinctive elongated structure. Fragmentation events provide unique scientific opportunities. Each fragment essentially represents a sample of the nucleus interior, suddenly exposed to space and immediately beginning to outgas. By comparing the composition and behavior of different fragments, astronomers can map internal heterogeneities and understand how the nucleus was structured. Different fragments might show different carbon dioxide to water ratios, revealing compositional gradients within the original nucleus. The most catastrophic scenario involves complete disintegration of 3I Atlas during perihelion passage, where thermal and mechanical stresses so thoroughly destroy the nucleus that it essentially vanishes, leaving only a diffuse cloud of gas and dust. This outcome, while disappointing from an observational perspective, would provide dramatic proof of the sun's power to transform interstellar matter. complete disintegration typically occurs when a comet nucleus lacks sufficient structural integrity to withstand the combined stresses of solar heating. Small nuclei, less than a few hundred meters, are particularly vulnerable because they heat through quickly, creating high internal temperatures and pressures throughout their volume. Rubble pile structures, loose aggregations of smaller pieces held together mainly by gravity and weak ices, are also vulnerable because they lack the structural strength to resist fragmentation. The process would likely be rapid. As the nucleus heats up approaching perihelion, outgassing rates would spike dramatically. Internal pressure would build faster than it could be released through surface pores and cracks. At some critical point, the structure would fail catastrophically, with the nucleus essentially exploding into a cloud of debris. Within hours or days, the cloud would disperse, becoming too diffuse to observe. From Earth's perspective, observers would see 3I Atlas brightening dramatically in the days before perihelion, perhaps becoming visible to the naked eye, then suddenly fading as it rounds the sun. Post-conjunction searches might find only a faint, diffused nebulosity at the predicted position, or nothing at all if the debris has dispersed completely. While such an outcome would eliminate opportunities for detailed post-perihelion studies, it would provide unprecedented data about the thermal and mechanical processes that govern cometary destruction. The brightness curve, how quickly the comet brightened and then faded, would constrain models of sublimation rates and structural failure. The composition of the debris cloud would reveal what the nucleus was made of. The rate of dispersal would indicate the velocities at which material was ejected. Finally, there's the possibility that keeps some researchers up at night. What if 3I Atlas exhibits behavior during perihelion that cannot be adequately explained by natural physical processes? This scenario encompasses a range of potential observations that would suggest the object might be something other than a simple interstellar comet. Unexpected trajectory changes would be the most obvious anomaly. Natural comets experience non-gravitational forces from asymmetric outgassing, but these forces are generally small and predictable based on the comet's activity level. If 3I Atlas showed trajectory changes inconsistent with its observed outgassing, particularly if it accelerated in directions that don't align with solar radiation pressure or typical outgassing patterns, it would suggest active maneuvering or unusual propulsion mechanisms. Unusual electromagnetic emissions would be another red flag. Natural comets produce radio emissions when the solar wind interacts with their ionized comas, but these emissions have well understood characteristics. Detection of narrowband radio signals, organized patterns of emission, or signals at frequencies unusual for natural sources would warrant serious investigation. SETI researchers have suggested that technosignatures, signs of artificial technology, might be detected from interstellar visitors if they contain active communication systems. Geometric structures or surface features inconsistent with natural processes would be compelling evidence. If high-resolution imaging, perhaps from Parker Solar Probe during perihelion, revealed straight edges, regular patterns, or other features suggesting artificial construction, it would fundamentally change our interpretation of the object. However, achieving sufficient resolution to detect such features is technologically challenging given the object's size and our limited observation opportunities. Unusual thermal behavior might be detectable through careful infrared monitoring. Natural comets heat and cool in predictable ways based on their rotation, surface properties, and distance from the Sun. If 3I Atlas showed temperature distributions that couldn't be explained by solar heating alone, hotspots in shadowed regions, or temperature variations that don't correlate with sunlight exposure, it might indicate internal heat sources or unusual thermal properties consistent with artificial materials. It's crucial to emphasize that this scenario remains speculative. All of 3I Atlas's observed properties to date can be explained by natural processes, even if some explanations are uncomfortable or require invoking unusual conditions. The scientific approach requires that we look for evidence of anomalous behavior without presuming it exists, maintaining rigorous standards of evidence while remaining open to surprising discoveries. Perhaps most profoundly, 3i Atlas forces us to confront our cosmic isolation and connection simultaneously. This ancient wanderer has travelled for millions or billions of years through the vast emptiness between stars, carrying with it the frozen remnants of processes that occurred when our solar system was young or perhaps not yet formed. Its arrival in our cosmic neighbourhood represents a tangible connection to the broader galactic community of stellar systems, a reminder that we exist within a vast ecosystem of stellar birth, evolution, and death. The galaxy contains roughly 200 billion stars, most of which likely host planetary systems. Computer simulations suggest that planet formation is a violent, chaotic process that produces enormous amounts of debris, far more mass in small bodies than in planets. Much of this debris gets ejected into interstellar space during the early stages of planetary system evolution. The galaxy might contain trillions of interstellar objects, ranging from small dust grains to planet-sized bodies all wandering between the stars. These objects form an extended debris field, pervading the galaxy, a vast reservoir of material that connects stellar systems across light years. Occasionally, our solar system's gravity captures one of these travelers, giving us a brief opportunity to study matter from alien star systems. We're essentially sampling the galaxy's debris field every time an interstellar visitor passes through, learning about the diversity of planetary formation processes occurring throughout our cosmic neighbourhood. The mystery of 3i Atlas's upcoming perihelion passage embodies humanity's eternal struggle to understand our place in the universe. We are a young species barely beginning to develop the technological capabilities necessary to study such cosmic visitors. Yet we find ourselves witnessing events that connect us to the deepest processes of galactic evolution. Every photon of light we collect from this ancient traveller represents information that has journeyed across unimaginable distances and timescales to reach our instruments. Consider the atoms that make up 3i Atlas. The hydrogen was formed in the Big Bang roughly 13.8 billion years ago, when the universe was just minutes old. The heavier elements, carbon, oxygen, nitrogen, and others, were forged in the nuclear furnaces of stars that lived and died before our sun was born. These stars, their names unknown and unknowable, enrich the interstellar medium with the raw materials for new stellar generations. As we conclude this exploration of 3i Atlas and its approaching rendezvous with destiny, we're left with more questions than answers. Will the comet survive perihelion intact, providing unprecedented insights into how interstellar matter responds to stellar heating? Will it fragment into multiple pieces, revealing its internal structure through catastrophic disassembly? Will it vanish entirely in a cloud of gas and dust, demonstrating the awesome power of solar radiation to transform ancient ice? Or will it exhibit behavior that challenges our understanding and forces us to reconsider what we thought we knew about objects traveling between the stars? The observational blackout imposed by solar conjunction means we'll have to wait patiently for answers. In early November, as 3i Atlas emerges from behind the Sun and becomes observable again from Earth, telescopes worldwide will search for the comet and assess how it has changed. The first post-perihelion detections will be crucial. Is the comet brighter or fainter than predicted? Does it show a single condensed nucleus or multiple fragments? Have its spectroscopic signatures changed, indicating that new material from the interior has been exposed? Whatever we discover will advance our understanding of these cosmic messengers. Each interstellar visitor provides unique data points, constraining our models of planetary system formation, galactic dynamics, and the physical processes governing small bodies. With only 3 confirmed interstellar objects detected so far, every new observation significantly impacts our statistical understanding of these populations. Looking beyond 3i Atlas, we can anticipate a future rich with discoveries. Next-generation survey systems will detect interstellar visitors regularly, building catalogues large enough to identify patterns and trends. We'll learn which types of compositions are common and which are rare, how ejection velocities relate to object properties, and whether trajectory alignments, like 3i Atlases, are genuinely anomalous or simply reflect selection effects in our detection methods. Space missions to interstellar objects, while technically challenging, appear increasingly feasible as detection methods improve and mission concepts mature. Within decades, we might see the first spacecraft encounter with an interstellar visitor, providing close-up observations and perhaps even sample return. Such missions would transform our understanding from remote observations to direct physical investigation, revealing details invisible to even the most powerful telescopes. The study of interstellar objects bridges multiple disciplines: astronomy, planetary science, chemistry, astrobiology, and even the search for extraterrestrial intelligence. These visitors connect us to the broader galactic community of stellar systems, carrying information about cosmic processes operating throughout the Milky Way. They remind us that we live not in isolation, but as part of a vast, interconnected cosmic ecosystem where matter flows continuously between stars. As October 29th approaches and 3i Atlas makes its closest approach to our Sun, somewhere between Earth and Mars, billions of years of cosmic history will culminate in a brief, intense encounter. Ancient ice formed around an alien star will experience the warmth of our Sun for the first time. Material preserved in deep freeze for eons will sublime into space, its molecular structures finally revealed to our instruments. Thermal stresses will test structural integrity developed in environments we can barely imagine. And we will watch, as best we can, given the observational constraints, trying to understand what happens when matter from one stellar system encounters another. We will measure, analyze, model, and debate, gradually building understanding from fragmentary observations and theoretical insights. We will argue about interpretations, propose alternative explanations, and design new observations to test competing hypotheses. This is science at its finest, humans working together across national boundaries and institutional affiliations, united by curiosity and the drive to understand nature more completely. The questions raised by 3i Atlas will occupy researchers for years, spawning doctoral dissertations, scientific papers, conference presentations, and public lectures. The data collected will be analysed and reanalysed as new techniques and theories emerge, and through it all, 3i Atlas will continue its journey, receding from the Sun after perihelion and eventually leaving our solar system entirely, returning to the interstellar void from which it came. Decades from now, it will be so distant that even our most powerful telescopes can no longer detect it. Centuries from now, it will have travelled light years away, perhaps approaching another stellar system where, if circumstances align, alien astronomers might detect it and marvel at this visitor from the depths of space. But for now, in these final days of October 2025, 3i Atlas belongs to us, or rather, we have the privilege of observing it during its brief passage through our cosmic neighbourhood. The ancient wanderer that has travelled farther than human imagination can fully grasp, is giving us a fleeting opportunity to study matter from another world, to expand our understanding of the galaxy we inhabit, and to contemplate our place in a universe far stranger and more wonderful than we ever dared imagine. The countdown has reached its final hours. The mystery deepens even as solutions begin to emerge, and somewhere in the space between Earth and Sun, invisible to our eyes but tracked by our instruments, 3i Atlas races toward its appointment with our star, carrying questions that may reshape our understanding of what travels between the stars and our place in the vast, ancient, and possibly populated universe we call home. Thank you for joining me on this journey to the edge of known physics and the beginning of new understanding. The universe has presented us with another mystery, another opportunity to learn, another reminder that reality is far more fascinating than fiction ever could be. Whatever happens next, we are privileged to witness it, to be the generation that first began to routinely study visitors from other star systems and to ask what their presence teaches us about the galaxy we inhabit. Keep watching the skies. The universe has more surprises waiting for us, more mysteries to unravel, more wonders to discover. And who knows, perhaps among those future discoveries will be evidence that we are not alone in asking these questions, that other minds under other suns are also looking outward, also wondering, also trying to understand the magnificent cosmos we all share. 3-Eye Atlas, the cosmic mystery approaching our sun.